Yeah, I guess we can start. Okay, so it's my great pleasure to introduce Paul Chleboun from Warwick, and he's going to talk to us about the mixing time for the facilitated exclusion process.
Yeah, thank you very much, and thank you for having me. So hopefully I don't bore you too much with an introduction on what this facilitated exclusion process is, and then we'll move on to the mixing time in a few different cases. Okay, so the facilitated exclusion process is a sort of kinetically constrained model in the sense that particles can only move if the local environment satisfies a certain constraint. In particular, it looks like a simple exclusion process, except for some extra constraint on the particle motion. So it was originally introduced in the physics literature to study universality in active absorbing phase transitions, so systems that undergo an absorbing phase transition. Okay, and the idea was that it was in a different universality class from directed percolation, which most of the other models were in. But more recently, there's been a lot of interest around this model, in particular related to the hydrodynamic limit, and the interesting sort of Stefan problem that arises for the hydrodynamic limit by authors, some of whom are in the room. Okay, so moving on, what is the facilitated exclusion process? So for the talk, I'm going to just look at one dimension and a finite number of sites. So the number of sites I'm going to call n on a one-dimensional lattice. It's a simple exclusion facilitated exclusion process in the sense that we only look at nearest neighbor jumps. It's exclusion in the sense that you can have at most one particle per site. And then there's going to be constraint on top of the usual exclusion process rates. So I've written the sample space here. And as usual, we think of a particle at a site as being represented by a 1. Okay, so firstly, exclusion means that particles can't jump on top of a site that already contains a particle. The constraint is that you need a particle behind the particle that's trying to move in order to be able to move. So isolated particles are stuck. They can't move. You can only move if there is a particle behind you to push. That should be on the next slide. So in particular, the only particles that can move in this configuration down here are these two. Okay, and in the asymmetric case, in general, a particle then jumps to the right with probability rate P, and it jumps to the left with probability rate Q. Okay, and here I've written the generator. So in particular, for a particle to move from site X, there has to be a particle at site X. There has to be a particle behind it if it's moving to the right. And the site it's moving on to must be empty. Okay, I should stop at this point. So I guess that's the process defined. So is the process in one dimension clear to everybody? Good. I don't see any questions. So moving on. So we consider this process with a fixed number of particles on n sites where we consider the boundaries closed. So I'll call that the closed boundary or the interval process. So we don't consider the case where particles can enter or exit this closed interval. The number of particles is conserved. So that's one situation we'll consider. We'll also consider putting this process on the one-dimensional torus, so periodic boundary conditions. If we can move this picture. So that is site 1, so particles can jump from site 1 to site n and vice versa. Good, so that's the two situations we'll consider, and in particular, we'll look at both symmetric and asymmetric on the closed interval, and on the torus, we'll only consider the symmetric situation. The point is that in all the situations we consider the dynamics, there exists a unique reversible stationary measure. Okay, if the total number of particles is less than or equal to n over 2, then the system will eventually reach some absorbing state, right? So eventually all the particles will spread out so that they're all isolated. And in this case, you're stuck in an absorbing state. So if the total number of particles is smaller than n over 2, the system's sort of trivial in that you just wait till you hit an absorbing state and then you're stuck there forever. So the interesting situation for the mixing time is, okay, it's clear there's no coming back. The case we'll be interested in is when the total number of particles is strictly bigger than n over 2. So in this case, you eventually reach some ergodic component. That is, there exists a unique invariant measure. And in this case, where it's either closed or it's symmetric on the ring, the dynamics on the ergodic component are reversible. So we don't consider this case of asymmetric ring, because then there's a current and the process isn't reversible and the techniques we have won't work. Okay, so if you start from some transient state, like this one here, with all the particles jammed up close to site n, then eventually you have to wait until the process has reached the ergodic component, and then you have to mix on the ergodic component. So what does the ergodic component look like? If you consider the case of a fixed closed system, then eventually there'll be a particle at either end. Can I move this up here? Yeah. So eventually there'll be a particle at either end. Once a particle hits site 1 in the closed case, it can never leave because we consider the outside as being empty. So eventually particles will be absorbed at either end. And then the ergodic component is just described by all the configurations where particles are separated by no more than one empty side. Right? If you have a separation of 2 or more empty sites, eventually it'll close and you can never create a gap any bigger than this one empty side under the dynamics. Okay. Everyone still happy? Good. Okay, so that's the ergodic component on the interval. Similarly, the ergodic component on the ring is a little easier to describe. It's just all the configurations where particles are separated by no more than one empty site. Okay. Good. So as I said, in both these situations that we consider, the dynamics on the ergodic component are reversible. We can write down the reversible measure. We don't have to worry too much. It'll be clear later where this structure comes from in a more intuitive way. As I say, on the one-dimensional torus, we only consider symmetric dynamics. And in that case, the reversible measure is just uniform on the ergodic component. Good. Okay, so then what are we interested in? We'd like to understand the mixing time. So how long does it take, started from the worst case initial condition, to reach the reversible measure, to be close to the reversible measure? So in this case, we could look at the spectral gap of the generator, i.e. the inverse of the spectral gap being the relaxation time, but this will not tell us anything about how long it takes the process to leave these transient states. So we want to know what is the total variation mixing time started from the worst of the transient states. Okay, so we look at the L1 mixing time in the usual sense. So I've just written down the total variation. definition of total variation distance here. And then what we're interested in is how long does it take? So small is t, such that the distance between the law of the process at time t started from the worst case initial condition, and the equilibrium, the reversible measure, is smaller than or equal to epsilon. So presumably most people here are familiar with the total variation mixing time. Again, I'm going pretty rapidly, so do shout up or stick a hand up or let me know if anything is not clear up until this point. Okay, so this is the object we're interested in these two situations. So closed interval or on the torus.
Sorry, Paul, if you don't mind, a stupid question.
Yep.
So why, as I'm by no means a specialist of mixing time, but so d of t is continuous in t, right?
Yes.
So t mix is just the inverse function of d of t, no?
Yeah.
Okay, so my question is, usually the mixing time is defined this way, and I guess there is a reason, but I wonder if, I mean, what is the reason for this presentation rather than just saying, okay, the mixing time is just the inverse function of the total variation distance?
Okay, good question. I mean, to define it, so at least with this definition, you don't have to prove that it is the inverse function.
Okay,
right?
yeah,
So
that's a fair point.
You'd have to first, okay, it's true in general, but you have to prove the continuity of dt and that it's monotonically decreasing and weakly decreasing. Okay. So yeah, okay, I think just for convenience of having a robust definition.
Okay, thanks.
Okay. Good. Okay, so a quick detour on cutoff, which simply because this would be a nice thing to prove for our models, but we can't do quite as well as cutoff. So again, I think most people here are probably familiar with this idea, but okay, as we just mentioned, so the distance started from the worst case initial configuration. The distance from the stationary distribution is decreasing. So this idea of cutoff says that the window over which this total variation distance shrinks from being close to 1 to being close to 0, this window is growing slower than the total variation mixing time itself. It's of lower order. So this arises surprisingly frequently in many models. Okay, our understanding of it is becoming more robust, but a lot of things we know are essentially just by case analysis. But anyway, so here's the picture of what it means for a model to exhibit cutoff, as in it means that the limit, as we look at the larger and larger systems, of the ratio of the mixing time at epsilon and 1 minus epsilon is 1. That is, so to leading order, this mixing time is independent of the parameter epsilon. Okay, so this gives us some, if we could show cutoff, it would give us some very detailed information about how the process is converging to equilibrium. For none of the situations I've described so far can we show something as strong as cutoff, but we can show free cutoff, which is necessary but not sufficient for cutoff. So in particular, okay, the ratio of the mixing times at epsilon and 1 minus epsilon is bounded uniformly in epsilon. So that is, so there exists constants independent of epsilon such that we can bound the leading order of the mixing time above and below by these constants. Okay. That was our whirlwind tour of cutoff and pre-cutoff. Okay, The problem with talking to a screen is I realize I go super quickly. So please, anybody shout up if it's too fast. But maybe I'm boring people. Okay, so then what are our results? So if we look at the symmetric facilitated exclusion process on a closed interval of n sites and k particles, where k is strictly bigger than n over 2 and strictly smaller than n, then essentially the total variation mixing time goes like n squared log n minus k. So this is the number of holes in the system. And we have 3 cutoff. And we would conjecture there is cutoff, but we can't show it. And in a moment, we'll discuss why. Okay, so you should compare this. So this, it's not a coincidence that this looks a lot like the mixing time you get for the simple symmetric exclusion process on the interval, for which a similar result holds. Okay, here we have k instead of the number of holes, but otherwise it's the same. Here the constant is known, we don't know the constant, and in that situation, cutoff has also been shown. Okay, but it essentially looks like the mixing time of the exclusion process. Whereas if the process is asymmetric on the closed interval, then started from the worst case initial condition, actually the mixing time is growing exponentially in the system size. And this is due to essentially some metastable behavior that occurs if you start from the worst case initial configuration. And this, again, to contrast with the asymmetric simple exclusion process on the interval, is very different. So the asymmetric simple exclusion process on the interval mixes in a time which is of order n. Here, this is exponentially slow. But what's going on here is this mixing time is completely dominated by how long it takes for the worst case initial configuration to reach the ergodic component. And then on the ergodic component, again, for reasons we'll see in a moment, we look like the asymmetric simple exclusion process anyway, and it mixes extremely fast. So this exponentially slow mixing time in the asymmetric case is due to this hitting time problem of reaching the ergodic component started from the worst case initial configuration. Okay. And I've already hinted at it. So the way we approach this problem is to essentially break it down into the 2 subproblems. That is, first, how long does it take to reach the ergodic component starting from bad initial conditions? It's essentially a hitting time problem. And then secondly, once you're on the ergodic component, how long does it take to mix? And in particular, once we're on the ergodic component, we'll see that it's essentially just reduces to the analogous exclusion process. So simple exclusion process, either asymmetric or symmetric, depending on the situation we're in. Okay. It's not, so that's true on the closed interval. It's not quite true on the ring, but we can do similar comparisons. So that's the whole point then of the rest of the talk, is the proofs are essentially just lots of couplings and comparisons with well understood processes. So including simple exclusion process, open boundary exclusion process, zero range processes, and mostly the couplings are through a height function. So something that looks similar to the usual lattice path you have for the simple exclusion process. So in particular for the closed interval case, once we have this picture in terms of the lattice path, we can couple all these sort of different models that are already well understood with our process. And from this, we just extract the results from the literature, essentially. There's nothing too deep apart from these comparisons. Okay, good. Okay, and the intuition dates back to at least 2010, if not earlier, when this model was first being studied. And the intuition is as follows. So imagine we have here a configuration of our facilitated exclusion process. For our facilitated exclusion process, now if we go along and we just draw boxes around all these dimers that are a particle on the left and a hole on the right. So we have these red boxes are our particle hole dimers. These particle hole dimers themselves move according to exclusion dynamics once we're on the ergodic component. So that is, if this particle here in the facilitated exclusion process, this one can move to the left because there's a hole behind it, and there's a particle on the right of it. So in particular, this one here can move to the left. And when it does so, that's the same as this dimer moving to the right. Okay, so maybe you just have to stare at this picture for a little while to spot that you can't create or annihilate these dimers once you're on the ergodic component, and the dimers themselves move according to an exclusion process, but an exclusion process where the particles are now of size 2. Okay, so with this in mind, it's essentially the intuition for most of the proofs, along with some monotonicity, stochastic monotonicity that we inherit from this height function that I'll try to define now. So first, we're now considering just the facilitated exclusion process with on the closed interval. And I'm going to define this height function for any configuration of the facilitated exclusion process, whether it be on the ergodic component or not. And to define it, so for a given exclusion process, facilitated exclusion process configuration, I first order the particles from left to right. So I've got particles labeled 1 up to k. K is the total number of particles. And I call xi the position of the ith particle. Okay, so that's going on down here. So this is my facilitated exclusion process configuration. Particle 1 is at site 1, particle 2 is at site 3, particle 4 at site 4, etc. Okay, then I define the height function as follows. So first fix the height of the leftmost point simply to be 2 times the first position minus 1. So in the picture down here, it starts from 0 because there's a particle already at site 1. And then you go up by 1. So okay, the change in the height between the first eta, the height function at 1 and the height function at 2 is given by twice the number of empty sites between the I plus 1 and the ith particle minus 1. So in particular, if there's 1 empty site between the first particle and the second particle, then we go up by 1. If the second particle and the third particle are neighbors, the number of empty sites between them is 0, we go down by 1. If there are 3 empty sites, then we go up by 3. That is because, okay, the number of empty sites, sorry, if there's 2 empty sites, we go up by 3. Right? It's twice the number of empty sites minus 1. So the reason we define it like this is because the only place the height function can change is at local min and local max. And every time a particle moves is the same as moving a local maximum down by 2 or a local minimum up by 2. So, okay, for people who are familiar with the writing down height functions for the exclusion process, it's similar. Let's look at an example. So this is what I said. So this particle in the facilitated exclusion process can move to the left with rate q because there's a particle behind it and an empty site. Sorry, there's a particle in front of it and an empty site behind it, which corresponds to, at rate q, this local maximum moving down by 2. Okay. So an important distinction between this height function and the one sort of analogous one you'd cook up for an exclusion process, there can be steep upslopes. There are never steep downslopes. This downslope is always at most, or rather at least -1, so at most 1. But there can be steep upslopes. But if you reduce the gradient of this steep part, it can never increase again. Okay. I'll try and convince you of all these things through examples, but essentially you have to take my word for it or just stare at the model for long enough that this becomes clear. So the point of doing this then is that we can couple our process, our original facilitated exclusion process, with started from any initial condition with just flips for the lattice path. So we just think that at every site in the lattice up here, we have a Poisson clock for flips down and a Poisson clock for flips up. Every time a clock rings, you check if you're at a local maximum and it's a ring corresponding to a flip down, you can do it. If you're at a local minimum and it's a flip for a ring up, then you can do it. Otherwise, at all the other rings, nothing happens. So it's a very useful way of coupling all our initial conditions, and not only that, but also facilitated exclusion processes on intervals of different size and things like this. Okay, so in this next example, the number of empty sites from the boundary here up to the first particle is 3. Remember, we start at 2 times this number of empty sites. So in this case, it starts at 6. And the only thing that can happen to this leftmost particle in the facilitated exclusion process, okay, it can first move to the left, in which case this goes back down again, but then it can never go back up again because there's never a particle on the left of it. So in particular, the boundary dynamics are such that it can only ever be decreasing on this boundary until it hits 0, and it can only ever be increasing on this boundary. Okay, I'll stop at this point because I realize it's not the clearest presentation of the height function I've ever given. So do shout up if this definition of this height function is not clear. The important thing is that there's these steep parts that can go away that correspond to big gaps that must be closing. Once we reach the ergodic component, all these big gaps have closed and you have gaps of at most 1 empty site between all the particles. In particular, once we're on the ergodic component, the height function looks like the height function that you could construct for a simple exclusion process. And again, this is because the I've written my timers the other way around now, sorry, but either the whole particle or the particle whole dimers, once you're on the ergodic component, move according to a facilitated exclusion process. The fact that they're now of size 2 doesn't really matter once we've reached the ergodic component and we have closed boundaries, because given any sort of exclusion configuration where you just shrink each of these to size 1, you can reconstruct it's bijective with the dimer picture just by growing them by size 1, starting from the left. So, okay, so it was already clear, but now we have a nice height function representation that once we're on the ergodic component looks like the height function of the exclusion process. The nice thing though is that this new height function is the dynamics with respect to this new height function. So it's bijective, or rather it's injective, so bijective on the image. So we can fully describe our process just by looking at the height function. And the dynamics of the height function under the coupling that I briefly described earlier, these flips of local minimum and local maximum, is stochastically monotone. So if we start from, so we can couple our dynamics starting from any initial condition. If we start from an initial condition that's initially two initial conditions, one of them has a height function strictly smaller than the other one, everywhere less than or equal to the other one, then this monotonicity is preserved by the dynamics, this coupling in time. Okay. It should be at, not 8. Okay, is the coupling and the height function dynamics, are they all clear? Okay, good. So then obviously once we have this height function representation and this stochastic monotonicity, in order to bound the mixing time, we can compare with the usual coupling time. That is, start from the maximum and minimum configurations with respect to this partial order we have on height functions. And as long as we understand how long it takes to couple the maximum and minimum configurations with respect to this partial order, this will give us a bound on the total variation mixing time. Okay, so in particular, once the maximum and the minimum couple under the construction, so that these two meet under the construction I gave earlier, then everything else remains sandwiched in between, so everything's coupled, so you get a usual bound on the total variation distance in terms of the coupling. Okay, again, people have probably seen bounds on mixing time using these coupling arguments before. Good. So this is a slightly complicated looking slide. Maybe I can even zoom in. So the point is that this eta plus is the maximum with respect to the partial order on height function configuration of the facilitated exclusion process with closed boundaries, and it corresponds to the configuration on the top down here, where all the particles are stacked up at the right-hand side. So the height function for that is this height function that starts at maximum height here, and then just goes down with slope 1 to 0. Okay, so that's the maximal configuration, and equally the minimal configuration is all the particles stacked up on the left. And the other two configurations that are drawn here are the maximal and minimal configurations on the ergodic component. So ones whose have height functions that look like simple symmetric exclusion process height functions. Okay, and then the way we do the argument is essentially in 2 steps. We first look at how long it takes for the maximum height function to reach the ergodic component and the minimum configuration to reach the ergodic component. And then we can look at the amount of time it takes to couple the maximum configuration and minimum configuration with respect on the ergodic component. So as I said, so this is back to what I said at the beginning, it's essentially a 2-step argument. First, how long does it take for these two to reach the ergodic component? And then how long does it take for these to couple? And the second thing is immediate from results that are already known for the exclusion process. So really, we just have to bound how long does it take for this maximal and minimal configurations to reach the ergodic component. And that's this starting from everyone stacked up at one side, how long does it take one to go all the way to the left, or how long does it take for the last particle to go all the way to the right? Okay. And now comes the comparison with the open boundary simple exclusion process. So if we start from the maximal configuration for the facilitated exclusion process, the only thing that can happen initially is this particle on the left can move left by 1, which corresponds to introducing a dimer on the right of this particle. The dimer then moves with exclusion-like dynamics in this region. You can't introduce another dimer until this one has moved away, which corresponds to this particle here moving left 1. That corresponds to the dimer moving to the right 1. In that case, you put a particle behind the leftmost particle here, and this guy can move again. That corresponds to introducing. So, okay, that's what it said. So this, currently the only thing that can happen is this particle here can move left by 1. When he does so, he becomes a right neighbor of the leftmost one here. So he can either move back, or this leftmost particle can move left again, which corresponds to introducing another dimer. Okay, so hopefully proof by pictures I've convinced you what's actually going on here is if we just think about the dimers to the left of the to the right of the leftmost particle, then what we have is an open boundary, open on the left, simple exclusion process, where again we just shrink down the size of our dimers to be size 1. Okay, so once we've made that comparison, which, okay, we can make it more precise through the coupling we have with the height functions, but once we've made that observation, then we can write down very precise bounds on how long it takes to reach the ergodic component by using the results of Gunter, Nestoridi, and Schmidt for mixing times of the open boundary exclusion process. So now we've compared with an open boundary exclusion process, used previous results to bound how long it takes to move this leftmost particle as far as it needs to go so that we've hit the ergodic component. And then having done that, oh, that's the end. Once we're on the ergodic component, then we're equivalent to a simple symmetric exclusion process. So we just use the existing bounds on mixing time for simple symmetric exclusion process to get the coupling time. Okay, so moving on to the next part of the talk, I'm going to be looking at symmetric dynamics on the one-dimensional torus. And in this case, we can only control, so we have lower bounds on the mixing time, which are general, but to get upper bounds on the mixing time, we can only start from reasonable initial configurations. We don't currently have a method that works for any initial configuration. The troublesome initial configurations for us are ones where we have very many of these, what I'm calling ergodic blocks, containing a moderate amount of particles. So, okay, first, I've skipped a bit. What do I mean by an ergodic block? So if we start the facilitated exclusion process on the ring from any initial configuration, then I define the ergodic blocks as being these maximal subsets where, restricted to this subset, the process looks ergodic. So in particular, there's a particle at either end in this block, and everywhere in between, there is at most one empty site. So outside of these ergodic blocks, there are just empty sites, and inside the blocks, the process looks already looks ergodic. Okay. Again, so sort of waffled that. Hopefully, so let me know if the ergodic block definition is not clear, but it's what you'd intuitively expect. We just split the any configuration up into the minimum number of sets, such that restricted to each of those sets, it looks like an ergodic interval. Okay, so the only case where we have good control of the upper bound of the mixing time is if we fix the initial number of these ergodic blocks to be independent of n and k. This is just a weakness of the way we treat the initial condition. And then what we can prove is that the mixing time essentially goes like n squared log n. So this is the same as for the simple symmetric exclusion process, except here we can't prove cutoff. We conjecture there is cutoff. And the problem we have for the upper bound is this controlling the hitting time of the ergodic component started from these bad initial configurations. Okay, so just for the sake of having some monotonicity, the first thing we can do is to map this facilitated exclusion process on the ring to a zero range process on the ring. This is not bijective. You lose some information about the sort of rotation of the original system. But the mapping is just that. So we start with the closest particle to zero, say, and then the number of particles on site zero in the zero range process is the number of particles to the right of this particle in the facilitated exclusion process. So we look at these blocks and we just sort of stack them up, and that gives us a zero range process. Okay, so that here we had an empty site corresponding to a new site in the zero range process. And then we have two particles corresponds to this stack of size 2. Another empty site corresponds to a new site in the zero range process. Then 4 particles in a row corresponds to a stack of size 4, etc. Okay, hopefully this is clear. The point is, so this zero range process now, particles exit a stack at rate 1 and then choose to go either left or right with the corresponding P and Q, unless there is a single particle at the site, in which case it's stuck. So once a particle, once there's one particle in that site, it's stuck forever. So the jump rate out of a site is given by the indicator function that the number of particles, beta at x, is strictly bigger than 1 times 1. So in particular, you can't jump out, right? So you start from something that's not ergodic, particles can fill up these empty sites and then get stuck there. Okay. The point is, once this zero range process has filled every site that corresponds to under this coupling, then necessarily the original facilitated exclusion process must have hit the ergodic component. Okay, this is useful because of an obvious monotonicity we get in the zero range process. I should say the facilitated exclusion process on the ring, one of the reasons it's much more complicated than on the interval is we have currently no nice representation in terms of a height function or a lattice path or anything. So this is the sort of easiest monotonicity we can dig out. Okay. Right. Then we want to know how long does this, so that we use that essentially just for some monotonicity. The way that we then calculate bounds on how long does it take to reach the ergodic component is essentially by splitting it into each of the ergodic blocks and waiting independently for each of the ergodic blocks to completely spread out. So if I first just look at this ergodic block by 1, I take this one, I sort of unravel it and embed it in Z. So I just take this block, I unravel it and look at the sort of corresponding facilitated exclusion process embedded in Z. So that is the leftmost particle here is this one, the rightmost particle here is this one. And now I just stick it in Z with all the sites outside are empty. Okay, so I just take this one and pretend all these sites everywhere else are empty. Now, what I want to do is just bound how long it takes for this ergodic block to completely spread out. If I wait sufficient time such that every block has spread out, then I know that I've reached the ergodic component. So this ergodic block, I've unwrapped it, I embed it in Z, and then again, this looks like an open boundary simple exclusion process. In particular, the particle holes move again according to exclusion dynamics. This leftmost particle here can move to the left, which corresponds to introducing a new dimer into the open boundary exclusion process. So I take this.
Sorry, Paul.
Yeah.
Another question. So you say that once all your ergodic clusters are spread out, then you've reached the ergodic component. But they don't spread out independently, right?
No, indeed. So
for example, on your drawing, the two on the left and on the right could try and spread out through the north.
Indeed.
And then maybe the bottom one could not manage to spread out in the bottom completely on its own.
Yeah. So indeed, and our approach to this at the moment is not very elegant. So we treat everything as being sort of separate, and rather naively, if you weight the amount of time it takes under this coupling for one of them to have completely spread out when you couple it to the dynamics on Z, then at that time, the number of ergodic components of the original system must necessarily have reduced by at least one.
Yeah.
It could be that this guy actually helped him to spread out, and the number of ergodic components reduced before that. Okay, sorry, I should say.
Okay, hence the finite number of ergodic segments.
Exactly, yeah, it's very naive and brute forcey. So I should say the number of active ergodic components reduces by one, right? Because this guy could completely spread out and not touch any of the others, and still look like an ergodic component, but not be able to move anymore, have absorbed. So every time you wait for this one to completely spread out under the coupling with the process embedded in Z, the number of original ergodic components you had that were active has certainly reduced by at least one.
Yeah.
Okay, it's, as you say, this is the reason why we have to restrict to a finite number of ergodic blocks, because this bound is, it's clear that you could do something more ingenious here and we haven't. Okay. So the point is, at the moment, we're treating them all separately and doing it inductively, where clearly they help each other. If there's very many, then they hit each other very soon and they help each other out. Good. Okay, so getting rid of that and just looking at the facilitated exclusion process embedded in Z, this is the mapping to the open boundary simple exclusion process, which is just the same as before now. As I say, so this particle can move to the right by one, which corresponds to this dimer moving to the left. This is the sort of corresponding picture of dimers. But the other thing that could have happened is this particle could have moved to the left. So in particular, this guy could move to the left, which corresponds to introducing a new dimer. Once the system is full in the open boundary simple symmetric exclusion process, and as I say, the number of ergodic components that are still active has reduced by at least one. Okay. So that's okay, and then bounds on that again is using the result of Gantet, Nestoridy, and Schmidt for mixing time of open boundary simple exclusion process. Then we get a bound on this, and it turns out, so even when we restrict to these nice initial configurations, the bound we have on this time is of exactly the same order as the bound we have on the mixing time on the ergodic component. So then moving to the second question, how long does it take to mix once we've reached the ergodic component? For this, we use bounds on the log Sobolev constant and comparisons with the simple symmetric exclusion process on the interval. So what's the trick here? Okay, first, but there's not enough time for people who haven't seen it. For people who've seen it before, this is just the definition of the log Sobolev constant. It looks like the usual variational principle for the spectral gap, only you will replace the variance with the entropy of F squared in the denominator. The numerator here is the Dirichlet form of the process. Okay, the point of using log Sobolev in this case is that we can do very direct comparisons with other processes because we just have to compare Dirichlet forms. So in particular, by removing transitions in the Dirichlet form, you immediately get a lower bound on this Dirichlet form, which would give us upper bounds on the mixing time. Okay. For those that aren't so familiar with log Sobolev, I don't think I have enough time to do it justice. So, but moving on, so the point is then using bounds on the log Sobolev constant. So in particular, so bounds on the mixing time in terms of the log Sobolev constant. So it's known in general that the total variation mixing time is bounded above. So a similar bound as you'd get from the spectral gap. So the inverse of the log Sobolev constant, the way I defined it, times, in the case of the spectral gap, here you'd have a logarithm of 1 over the least likely state under the reversible measure. If you have good bounds on the log Sobolev constant, this becomes a log 1 over the least likely state. Okay, for us, the reversible measure is just uniform. So the mu star here is just 2 to the n. So we pick up a log from the standard bound on log Sobolev, mixing time in terms of log Sobolev, but we just have to control the log Sobolev constant. And the way we do it is conditioning. So first, condition on the occupation of site 0, and then freeze it. And look at the dynamics with site 0 frozen. Say site 0 is occupied, and then from the Dirichlet form, just remove the transitions that involve this particle at site 0 moving. So I look at, I lower bound the Dirichlet form in terms of the Dirichlet form where this jump, all these jumps are removed. If I remove these jumps, then it looks exactly like the facilitated exclusion process on the interval, which is ergodic if you take this as being your right boundary. So in particular, we can compare again with the simple symmetric exclusion process, and good bounds on the log Sobolev constant for the simple symmetric exclusion process are known. So that is, if I condition on here, eta at 0 is 0 or eta at 0 is 1, then on this subset of the state space, I have good control of the Dirichlet form in terms of the entropy from the log Sobolev constant of simple symmetric exclusion process. Okay, then all I have to do is also condition on something which is almost independent of this. So partition the space essentially perpendicular to this and get good bounds on the log Sobolev constant this way. And then using the result of SESI from 2001, which says if I have almost independence, then the log Sobolev constant, the entropy almost factorizes. Stop. So almost independence means entropy almost factorizes. So the thing that I condition on that's almost independent is the occupation of the particle at, say, n over 2. If I fix this one, then I get good bounds on the log Sobolev constant perpendicular to this. And then I use the result of SESI to say that, okay, I can control the Dirichlet form on each of the bits and then combine them. And that gives me control of the Dirichlet form in terms of the entropy everywhere. Okay. So there's nothing, for people that have seen bounds using log Sobolev stuff before, this is probably clear. For those that haven't, I realize it's gone way too fast to probably be useful. The point is simply that by conditioning on the occupation of a single particle, we again reduce to comparison with the facilitated, firstly, the facilitated exclusion process on the closed interval, and therefore, since it's on the ergodic component, with the simple symmetric exclusion process. And that gives us bounds on the log Sobolev constant. Okay. So it's probably clear what some of the interesting open problems are from everything that I've just shot through. So in particular, this, I think the first thing to tackle will be general initial conditions on the ring, because there the argument we have is very cheap, and it's clear that something better should exist, although it seems surprisingly difficult. Currently, we can only prove 3 cutoff in all the cases where we'd expect cutoff to hold, and this is because of the very 2-step process that we're using, first hitting time of the ergodic component and then mixing on the ergodic component. In a sense, you should be able to do, using the height function representation we've got, you should be able to do everything all at once and use sort of the techniques used previously in the literature for exclusion process to get cutoff. We didn't look at all yet at open boundaries on a interval. And we haven't looked at all yet at non-reversibility on the ring. Or higher dimensions. So in higher dimensions, the process, obviously, okay, you first have to define the process in higher dimensions, of which there's a couple of ways of doing it naturally, and then everything becomes very complicated. Okay, thanks.
Okay, so thank you very much, Paul. Maybe there are more questions. Okay, so it seems like there are no more questions, so everything was perfectly clear. Okay, so thank you very much, Paul, and well, good night/afternoon to everyone, depending on where you are.
Thanks. Yeah.
Thank you, Paul.
Thanks.
Very nice talk. Really nice talk.
Yeah.
Hello.
Milton?
Yeah, we had technical problems, so I wanted to ask a question, but the microphone was.
Okay, no problem.
I was muted at the. Okay, so. So the convergence to equilibrium happens in these 2 phases, right? So these 2 phases, if you want to prove cutoff, you have to understand which of the 2 phases is longer than the other, in a sense, right? Yeah. So what do you expect to be? One is longer than the other, or both are the same?
Good question. So at the moment, so all the bounds we have suggest that they're of the same order.
Mm-hmm.
In this case, so symmetric on the ring. So as I say, clearly, so there's one obvious case where it's different. Asymmetric on the interval than the hitting time. You have, it's exactly the reverse bias case for the open boundary exclusion process. So it's essentially metastable. So it takes exponentially long to fill up the open boundary exclusion process. And this is the sort of metastability. Once you hit the ergodic component, then it mixes extremely fast at order n. So that's the one case that's different. Everywhere else, it looks like they're comparable, which is why it's going to be hard to prove any cutoff. You really have to understand them at the same time, I think. What would be really nice for the on the ring is some sort of analogy of a height function, some sort of lattice path. Yeah, but to your question, I don't know. If I had to, it's on the ring, it's either that they're just always they're of the same order, or maybe the conjectured worst case initial configuration on the ring would be everything piled up in one place. So it's a one block of particles. But similarly, as for the zero range process, we can't show that this is the worst case initial configuration. And then maybe it takes, okay, I think it's still in the same order, but maybe this is sort of the dominating thing. Maybe this takes longer than mixing, but I think actually they're on the same order.
Okay, thank you.
I have a question.
Sure.
Paul, did you look at this process in the infinite volume? For instance, you put particles to the left of the origin, all full, and no particles to the right of it?
So we didn't, but it has been looked at before. In fact, so this is one of the situations that was studied first. And this is one of the places where this dimer picture was first used. So you can couple, if you start with all particles to the left and empty to the right, for example, then you can couple with an exclusion process again, because every time the front particle moves, you introduce a dimer, and behind the front particle, they interact.
So you can couple with exclusion also in this case.
But this
is a symmetric case. So the behavior of the first particle is the same as the exclusion.
Okay.
Thank you.
Any more questions? Okay, so thank you very much, Paul, for a very nice talk.
Thank you.
And bye-bye, everyone.
Thanks.
Thank you, Paul. Thank you, Clément.
Bye-bye. Thanks.